Thank you very much, James and Cara, for inviting me, but also for putting together this brilliant set of talks, and also for having the second edition of these WeSST seminars, which are incredibly good. So what I've set up today, I really want to go back to how you link model and experiment. So I will start by looking at, for example, something that Ian Taylor showed in the previous set of talks for WeSST, where he proposed to build digital twin of Tribomotor. And it's very lucky that Louise preceded me, because Louise explained very well that digital twin means you need to look at the system, but not just as it is, but in the way it evolves. And this, even a simple reproduction of a thermometer, means that you need to, first of all, know from scratch what the conditions are, what you're running on. Can you see my laser pointer? Yeah, perfect. Yeah. And then, but you also need to know quite a lot about the materials, the surface chemistry, lubricants, and so on. So in itself, even just building a model of this system is particularly challenging. Now, the problem is it gets even more challenging when you try and reproduce and look at the evolution of these systems, because if you look at the rubbing interface and if you dig into what might be happening there, there is a huge amount of information that is required, and you need to know, for example, what are the dominant conditions, whether or not there is lubrication, whether or not there is film forming, whether or not phase transformations are happening, and all sorts of mechanisms that need to be reproduced. This is what really makes making a digital twin of a tribological problem particularly difficult, and that's where this is really complex. It's one of these things that I don't think we'll ever manage to do in a fully exhaustive way, but all we can do is try. And what we try best, both from, I think, from experimental point of view and modeling point of view, is in order to get some chances of linking experiments and models, we must try to understand what are the mechanisms that we want to capture, what we think is actually key for a specific problem. And in order to do this, unfortunately for us, we will have to go and look at what happens at all sorts of scales. So if you look at what is available today in tribology, it's the amount of simulations you do across the scales is huge. You can start looking from all the way from quantum mechanics up to meter scales of models, because you want to understand really where the physics and the chemistry dominates the problem, which is literally here, and then understand how that affects the behavior here. Now, many of you have seen me talking about what happens here often enough, and in fact, both Stuart before me and Michael after me will probably cover the lowest of the scales, and so therefore today I decided to look up and look at how simulation and experiments can be put together when you look at the scales that cover microscopic length scales all the way to application. And I've decided to do that by looking at some particular specific applications. And one of them is something that I've been working on for the last couple of years. I really got intrigued by this because I think it's got all the features of a fantastic tribological problem, which requires hell of a lot of understanding. And I started looking at tribal electrification, looking at what actually happens is in a now well-known phenomenon that if you rub things together, you might, depending on the material you're rubbing, you might create charges, and these charges can be used to produce an electric field and current. And in particular, I'm looking at liquid-based devices. These are called triboelectrical nanogenerators because they become particularly important, especially because allow you to acquire energy or get some electricity from all sorts of environment. And the principle is it's fairly simple. You have a certain polymeric surface that over which there is a liquid, in this case water, running. This polymeric surface needs to be high up in the triboelectric series, which means the capacity of generating charges and shedding them needs to be very high. And then as the water comes by, so instead of having another solid really rubbing against that surface, if you get a liquid like water and this moves along the surface, you get a generation of charges and you can generate current. And that is, it's a fantastic opportunity because it allows us to look at how you could use this. And there's plenty of proposal on how you can exploit this. And most of them are, for example, in the field of looking at waves, exploiting the fact that as there is water sloshing in and out due to waves, you could produce energy. So this is very important because you could actually get system which are self-sustainable and get electricity on board in places where it's very difficult to get some. But also people have proposed this type of approach to get energy from rain, as well as looking at application in agriculture, where actually you can look at the varying weather conditions to generate electricity. And the reason why I really got into this is because, as always, some experimentalists threw something at us. And here is the group Lanjou from Professor Zhu, and he started doing experiments looking at generating some electricity using a specific tank. This is a liquid-based tank, and one of the things that he tried to do, so this is a very simple principle. You have a cylinder, you have your surface here, and then you generate electricity through closing the circuit on the other end. And as you slosh the water here, you can see water coming in and out of the contact, and therefore you generate electricity. Now, this is something that was already well known, but here what they played with is very interesting. They played with the surfaces. So they generated some very nice polypropylene surfaces, and they could control the surfaces of the system very accurately. So they could have a surface which had microtexture of the range of 10 microns in size, and they could actually, on top of that, they could put some nanopillars material, which are very, very tiny features of in the range of nanometer scales. And they could build system where they could superimpose these nanopillars right on top of the microtexture, therefore generating something that they called hierarchical structures. And what they did, they started looking at the effect of surface on this. So it's well known in the literature that in these systems, if you got a super hydrophobic surface, you improve your efficiency of the systems. But what they went and did, they started trying the different surfaces. And the idea was that as you look at the sloshing, as you see in these pictures here, the different surfaces tend to generate some current, and you can have some voltage associated to it. And one of the things that they did, they looked at the different surfaces, and as you can see here, they got almost no current for macrotextured surfaces. Interestingly enough, because they were actually supposed to be fairly hydrophobic. They got some level of electricity for flat, completely smooth surfaces, and then they started getting quite large signals, both for the nanotexture surface, only with the micropillars, and the hierarchical structure, where you stick nanopillars on top of the microtexture. And here the question came: so how is that possible? And what is the mechanism that is really related to this? And obviously, one of the things that we try to do here is exactly what you need to do when you start building a digital twin, or you're trying to do so. We started looking at the details. So if you look at the structures we have, the first structure you get at the macro scale, you see these cuboids. So these are cuboids that are distributed over the surface, which actually generate this 60 microns layer on the surfaces. And what we started to do, we started to reconstruct these for simulation by looking at a representative volume element that will contain enough of those for us to be able to reproduce a surface. And as you can see, the average size here is in the range of 5 to 10 microns. And the idea will be that you could just start by generating a volume that periodically reproduces this. At the same time, if you go down the scale, this is where the nanopillars that I was talking about before. These nanopillars are literally stuck on top of these cubes if they are in the hierarchical structure. Otherwise, they can be on their own. And here we're talking about nanometers. So the diameter of these pillars is below 10 nanometers. One of these clusters, a volume of this system that is representative of this of the surface is about 200 to 300 nanometers. So we're talking about really different scales. And the idea is that, again, if you want to understand what happens here, you need to get another volume that represents the behavior of those scales. And therefore, you need to look at the distribution, the spaces between the clusters, the spaces within the clusters, and start having a statistical description of the surfaces. Why do we need that? Now, we need that because in anything that describes wettability, which is exactly what wettability and how to wet the surfaces. Because remember, energy cannot be formed unless you start getting wetting and de-wetting. So in order to understand that, you don't stand a chance to do it with a continuum model. You need to go down to what happens at the different scales. So what we did, we look at different representative volume of different scales. And the idea to start with was to look at how the wetting happens at different scales, because you can actually start looking at, because the scales are so different. You're talking about nanometers to microns to large hundreds of microns, millimeter scales for the full droplets. Here you are, you have a chance to try and understand how to superimpose these scales to get a model that captures everything. So the idea is that if you look, for example, at the nanometer scales, one of the things you can do, you can start looking at what will be the level of pressure that you need to apply to a film of fluid for this system to go from a Cassie-Bassia state, where basically there's no penetration of the water within the pillars, to a Wenzel state. And this simulation allows you to do exactly that. And this, for example, shows that if you look at the pressure required for a Wenzel state to start in a system like this, you will need to go into the range of 100 kilopascal or so. And these are usually the type of pressure you don't get from sloshing water over a surface. Now, if you look at if you look down at the microstructure, this is the cuboids I was talking to you about before. And the idea, again, here you want to capture how much energy there is to pin the water surface over the unwetted surface. And for this, you can actually do quite a lot of very complex finite element minimization of the energy. And the idea is that if you look at the same scenario as here, here you see that the situation is very different. So here, even if you reach 200 pascals, 150 to 200 pascal, you start seeing these fronts being broken. So you actually start seeing a transition to a Wenzel state, whereby the water penetrates into the microfeatures. And once you know that, the idea is that, okay, you can build up this simulation in stacks. You almost like get information from the bottom of the scales all the way up, and you can start looking at the macroscopic response of the system. And you can look at the macroscopic response of the system in two ways. First of all, you look at it statically, and you try to do a simulation of what will happen in terms of a static contact angle for these droplets. And the idea in our simulation was to match the experiment to the model to understand whether or not our description of the microscopic scales was right. And here, if you look at the stacking of scales simulation, you see that for the very flat unstructured surface, you get a contact angle for this material of about 100. For the microtextured surfaces, you get actually quite a lot of quite good hydrophobicity. You get 141 degrees. For the nanotexture with the pillar, quite interestingly, you don't get as much. Again, it depends on the nitty-gritty details of what happens in the pillars. And for the hierarchical structural structure, as known from experiments, you get quite an extreme value of contact angle, which looks at as a super hydrophobic surface. And the idea is that this would suggest, if you think about it, that probably if you trust the static angle as being a good measure of what happens in terms of dynamics on the surface, the hierarchical will perform better than the microtexture, will perform better than the nanotexture. But we know that that is not what we see in the experiment. And in fact, to study this, you need to look at the dynamics of things. For example, you need to look at what happens when pressure is applied to this droplet, for example, which is equivalent to applying some pressure to the film for sloshing. And if you do this simulation for a droplet here, and if you start looking at in the experiments, what happens as you push down on these droplets, one of the things you notice is that if you do the simulation and the experiments in the range of penetration and pressure that you expect, one of the things you see in the microtexture surfaces, at the level of penetration and pressure that you expect, at a certain time, you see this collapse of the film that is caused by the microtexture basically losing, going into the Wenzel transition state. And this is exactly what the experiment showed. The experiment showed that if you go up in penetration and therefore in pressure, you start basically getting a complete change in the wettability of the system. And in fact, you have quite a lot of residual water. What does that correspond to? That corresponds to if water is on the surface and it stays on the surface, basically you don't get wetting in the wetting. So the water presence doesn't allow you to generate extra current. And that is not the case for the hierarchical surfaces, whereby even if you press down at quite significant pressures, you basically have almost zero hysteresis. So loading and unloading produces exactly the same results. And again, the simulation, the experiment match these very well. And the idea is that in some ways, this is showing how it is not just a static problem; it's a dynamic problem, and the dynamic problem is what governs the system. Now, we've almost forgotten everything about our system, but let's go back to our virtual prototype. So we have this cylinder, and we slosh it, and this system is obviously governed by how fast you slosh it, how much wetting in the wetting there is in the system. And if we go back to what we saw, our experiments were done at a specific frequency and a specific stroke length. So this is actually 5 millimeter stroke and 3 hertz. And in order to understand now the relationship between what happens here and, for example, the pressure dynamics that I showed you in the previous slide, one needs to go again into the details of the sloshing dynamics of a system. We need to know exactly how the moving of the surface happens in a specific filling ratio, which in this case it was 30%. And the idea is that from those models, you can back out the level of contact pressure you get at the wall. And if you compare the level of contact pressure you get at the wall and you relate it to the transition I showed you before, then you can see that the level of pressure we get are those that more or less are triggering the transition from the Wenzel state in this particular case. And this is what we think is happening. So what we think is happening is that you get wetting on the wall. You get in order to get the wetting, you need to get complete disappearance of the film region. And here you can actually come up with a map that says if you have a certain frequency of sloshing and you look at the dewetting time coming from the dynamics of this system. Now, depending on the system you have, looking at the untextured, the nanotextured, and the multi-scale systems, you see that these depends very much on the dynamics of the system. For example, for the untextured and the macroscopic and the macrostructured systems, you see that you will not have enough time for the system to be at the wetting on time. While for the nanotexture and the multi-scale structure, you see you're in the regime whereby there is enough time for the system to lose water completely. And in order to verify this, remember, we're still looking at models versus experiments. One thing you could do is to do some epiluflorescence measurements. So you look at the different textures and you start looking at, you put some dye in it and you start looking at the residual value of amount of dye signal you get, function of time. And as you can see here, if you look at the hierarchical micro nanostructure system, there is almost no residual film there. So when you actually look at the system, even after 30 minutes, there is just some tiny remaining evidence of water. If you look at the nanotextures, there is some signal now that you start seeing coming from the fact that nanotextures themselves are actually, you can actually get water in there if you get some local pressure rises in the system. So slowly you might see some percolation. But what you see is what actually happened in the macrotexture is very stunning. You can start seeing that the water really percolates through this network of systems, and you get the intensity rising. And even at 150 seconds, you basically lost your capability of dewetting. And in fact, you can again use surface tension analysis and the scales at which the surface is and reproduce with the model and try to understand with the model the probability density function distribution that you get in time with the intensity of the water remaining coming from the fluorescent signal. And you can actually do some models to try and understand how this distribution change in time, which in our case seem to be fitting very well with the system. And again, I'm not saying this is actually explaining everything here. I'm just telling you how important it is when you have a system to feedback what you know from the experimental structure. Here we've looked at experiments from characterization of the surfaces, multi-scale analysis, all the way down to even understanding how the film formation and the film stays on the surfaces. So the important is that, as Liz said, you need to look at the system as it evolves, but also you need to always currently try to go back to what the experiment tells you. Now, in the remaining time, which is not very much, I'm going to show you what happens even in other applications, this time more conventional things. I'm going to show you how you do modeling and engineering components, and again, how you relate these models to experiments. Very quickly, if you look at a system, typical systems in any, there are loads of journal bearings, but if you look specifically at crankshaft bearings, for example, in conventional engines, the chance of reducing friction is very large. And lots of people have done both experimental work and models to get there. So I'm going to show you two examples where we've actually tried to study these systems. And one is looking at the high performance Conrod big end bearing. So we're looking at how to model this system and understand its link to experiments. And the other one will be also on a similar system, but with texture surfaces. The importance when you do application level system is to make sure you pick up exactly the feature you need. So geometry is important, load is important. This is the actual loading on that system, and the representation of the film formation here is also very important. And if you try your best to do a model, you can start looking. If you have your bearing, which is here, you can start looking at how the system deforms. You can start looking at how the aerodynamic film forms throughout the orbit of the cycle. You can also look at how the asperity come into contact if you have a model that allows you to capture those. And the idea is that these dynamics are fairly easy to calculate once you've got a very robust model. But that robust model might not be enough for you to capture things all the time. So here, for example, on this particular bearing, what we knew is that there was some particular cavitation damage. So one of the things that we tried to do, we started looking at, so this is the bearing, we unwrap it at 360 degrees here, and we start looking at how different geometries have different effect on this system. One of the things you can see is that if you look at the average hydrodynamic pressure, there's not much difference if you change the tolerances of the component. And there is some differences in the, this is where you get asperity in contact. That usually happen at the very edge of these bearings. But one of the things that you notice is that you start seeing differences in the where the cavitation happens, and this is again integrated over the cycle, the region where there is most cavitation. So if you now integrate the information you have about cavitation with the information you've got about pressure and the evolution in time, one of the things you can start seeing, we came up with a cavitation damage index, which tells you the most likely region where damage will happen due to the cavitation in the system. And this seems to obviously the geometry seems to have a much larger effect here because it's a compounded effect of all this information, and that allows you to also tell you why the damage in this specific circumstance was actually expected and seen exactly at that location. One other thing that I was going to say, and that's the last thing I show you today, is what happens if you introduce texture. So in these bearings, one of the things that people do more often than not these times is to introduce some surface texturing, because it's been shown that introducing surface texturing on the bearing shell improves performances. And if you specifically look at these performances improvement, you need to first of all understand what is the effect of location. And in fact, you can actually look at experimental evidence of this by testing this system. And this is, again, where the connection with experiment comes in. You want to test this system. You want to throw the right information at it. And one of the key information that most of the time is very difficult to get is thermal effects. So one of the modifications that was done in this experimental setup was to include trying to get some thermal information, first with thermocouples, but then also looking at infrared mapping, thermal mapping. And this allows you to get all the extra information you need. So you can get information about the film thickness through capacitance or through ultrasounds. You can actually start getting information about the temperature in the system, and also the spatial evolution of the temperature in the system. And the idea is that if you have this information, this can start looking at the influence of speed has on the system. If you also look at this, it can tell you whether or not that with thermal maps you have the transfer mechanism is what you are trying to model, or if you need to, for example, look at very strong gradients of temperature within the film. And if you look at this system, if you have a comparison between non-texture and texture surfaces, one of the things that appeared clear is that with some texture profiles, you get up to 18% reduction in friction. If this is a typical Strebe curve, if you look at the mixed into hydrodynamic regime, you see a reduction. And the models we try to set up here, we're trying to understand why this reduction is there. And I'm not going to go into much into the details, but the model is a fairly standard formulation, but we use a very energy conserving finite volume formulation. We look at the cavitation in the mass conserved fashion, and we update the lubricant temperature conditions looking at the effective temperature. Therefore, we look at the proportion of heat dissipated into the system, and we the global temperature rise that equates to changes in viscosity within the system, as well as looking at both the effects that you get from the feeding pressure and the side edges. So, for example, the fluid flowing at the side edges that actually are very important for a system like this. Once you build this on into the model, you then need to capture the texture. And for this, you need to have the level of details in your system that allows you to pick up the features. That means computational power and efficiency of your code is very important. And then you need to reproduce exactly what is happening in the experiment. And here is what you see. Usually, if you look at the untextured surfaces, we have a very good matching for all the conditions in different loads and different speeds. And one thing you notice is for different loads, there is some deviation here, and you can see that the experiments are tailing off while the model doesn't predict this. And this is mainly due to the fact that you have the global temperature correction we use is probably not efficient, not good enough for larger speed simulation, where you have thermal gradients across the film. Similar story happens for the texture. You get a similar prediction where a good correlation between the model and experiment. And the last slide shows you why we think texture provides the benefit that you see in the experiment. And this is, again, showing you a comparison in the film thickness, the pressure, the film fraction, and the shear stress at the surface for this system. This is without the texture, and this is with the texture. One of the most important differences is here. If you look at the shear stress, the system, the shear stress in the untextured has got a fairly benign variation, while obviously the introduction of texture exactly where the cavitation starts changes completely the scenario. You get a lower shear stress in the texture due to the fact that you have the larger depth of fluid, and then you actually have lower shear stress also between the texture because you have cavitation starting. And if you look at this in 3D, this is actually roughly what happens. So this is what is the volume fraction of the system. This is a cavitated area. And as you can see, the texture affects the cavitation deeply. You get wider cavitation zones, and these are definitely responsible for the decrease in shear rather than, for example, a change in the pressure, right? The pressure doesn't rise at all, so you don't have an increased liftoff. In this case, it's all due to shear reduction. And in this respect, I will just conclude with one last slide to say that if you look at what opportunities there are in this area, there is tons of stuff that it's very important. I think one thing is always to link the physics and the chemistry to what we want. There is lots of potential in doing digital twins, but we always need to ask the right question and use the right tools. And I think to me, the most important thing is always thinking that we need to talk more. We need to talk more. Material scientists, computational scientists, chemists and physicists need to get together to provide all the information we need for those models. And with that, I'll take any questions.